Good afternoon. Today we will talk about another type of derivative, an important concept in calculus 3, as you will see, the so-called directional derivative. And after we finish this topic, you will see that the partial derivatives we learned before are in fact particular cases of the so-called directional derivative. Just like in calculus 1, when you study the concept of a derivative of a function, I'm sure your instructor at the time insisted on the definition and how the tool is built, more than in the beginning, at least more than how you actually compute it. That's not to say that the computational rules are not important. They are, because if you use the tool quite often, you need to be able to differentiate quickly enough. But far more important is to understand the meaning behind the tool. Right, in calculus 1 cases, we talked about the slope of the tangent, rate of change of a function, and many other analogous interpretations of the first derivative. Kind of the same thing works here as well. We need to establish carefully what we mean, the definition, and then we get to the computational part of it later, which is actually quite simple, you will see. But we will take our time to actually introduce the concept and again connect it with the previous topics. So take a moment to sketch this picture here, and imagine that you have a function of two variables. By the way, the concept of a directional derivative is for any number of variables, but we will choose this one because it's easy to visualize. And then for simplicity, just assume the domain is the entire plane, xy plane. And we pick a point on the domain. And remember, the derivative of a function essentially is asking about the type of rate of change of the value of the function itself near the point or at the point AB. Remember, the derivative is a pointwise property. In the limit, you're looking at the limit of some sort of a difference quotient, so the rate of change of the function with respect to the change in the domain. So just to give you a little bit of a motivation, let's say, for simplicity, because that's easy to visualize, let's say the function in our story here is basically the altitude on a hill at the coordinate xy. So in other words, xy, let's say it represents the geographical coordinate, the latitude or longitude if you want. And then the function itself is the height or the altitude of the hill at that point. So using this analogy, what did the partial derivatives actually answer in terms of the what they tried to compute? Well, let's say you are right here on the top of the hill, right where the point F or AB is located. Okay, so like I said, the graph of the function is some sort of a hill. Just imagine, I don't want to make too much of a mess here, but that sits on a surface, right? The surface of the hill. And let's say you want to move in the direction, let's say north-south. Now, north-south with respect to the coordinate xy, right? With respect to the domain, in other words. North-south is like keeping the y coordinate constant at b, and then letting x vary, right? So that gives you basically a tangent whose slope is going to be which partial derivative? Pause for a moment and ask yourself the question. If b is kept constant and then you vary in the direction north-south, you try to move on the hill, you're essentially asking the question, do I go up or down if I move north-south? And that's given by the partial derivative with respect to x, right? The variable that still varies. I mean, the variable that still changes. So basically, in this interpretation, partial x at AB estimates whether you go up or down if you move north-south. And by the same token, let's say I move east-west, right? So around that point. Well, in that case, obviously a is kept constant and y varies, and therefore the slope of that tangent is going to be given by partial y at AB. So again, this will answer whether you go up or down if moving west-east or east-west. So I hope I hope you guys see where do I go with this, right? I mean, obviously, when we move on a hill, we don't have to move just north-south, right? So if I, look at the domain here and I'm at the location, geographical location AB, I can move north-south, I can move east-west, but really I can move in any direction around that point. And I can still ask the same question. If moving in any direction in the domain of the function, then what is the rate of change of the function f of xy at that point AB? So as you can see, actually, naturally, we have infinitely many types of derivatives because we have infinitely many directions. Fortunately, there is a single formula to compute all of them once you are given the point and the direction, which is the goal of this section. In any case, I hope it's clear in terms of what we're trying to answer. And with that in mind, let's actually make a slightly more formal picture to see how we actually formalize this in terms of math terms, right? I mean, how do we establish the definition of this so-called directional derivative? Now, notice to talk about the directional derivative, we need to specify the function, the point where I need to compute the derivative, and a direction on the domain from the point AB. By the way, just to agree with the notations from for the formulas later and what you will see maybe in books. Let's say the point in question is x naught, y naught. I should have chosen x naught, y naught to begin with. But let's say this is the point on the domain where we try to compute the derivative. And the direction, how do we measure directions or how do we represent directions in Calculus 3? You got used that up until this point. I hope that the vectors are the tool to go. Now, again, if we try to encapsulate just the direction of motion for which the magnitude is irrelevant, right? So we want an arrow to point in a direction of motion. The default tool is a unit vector. So that's a third quantity to be given in order to compute the directional derivative. So we're going to have to specify a unit vector in the component form, let's say with components AB. So therefore, like I said, the unit vector means the length is equal to 1. That's just standardization aspects. I mean, I think in some books, they teach you how to compute directional derivatives with vectors with any magnitude. But I think this is, it's logically, I think it's easier to just establish a formula for magnitude 1. And if the direction is given by a vector whose length is not 1, you can always normalize it and make it of length 1. Because if the magnitude is 1, the formula is pretty neat. That's one of the advantages of the whole thing. Okay, so let's sketch a slightly bigger picture here. And hopefully we can fit the definition in the same page before we worry how to compute it. Let's say, let's see if I have room here. So let's say this is the point, this is a point P. I'm going to name it P. I don't need that much the name, but just to refer it in the when I go over the formula. The important part are its coordinates, of course. So the point in question is x naught, y naught. Let's call it P. And here's the thing. We're going to exaggerate here a little bit the size of these segments. When we compute the derivative, remember, we're looking at a small change from P in the direction of U, right? Because we're going to have to take a limit of a difference quotient. Now remember, in Calculus 1, when you look at the definition of the derivative, you just take the point and then a nearby point, x naught plus h, and construct a difference quotient. And that h, remember, eventually means a tiny, tiny change, because once you establish the difference quotient, the derivative of the limit will be established by taking the limit as that h go approaching 0. So that h basically should be understood as a very small quantity, but for my picture to actually be easy to read, I'm going to exaggerate obviously the distance. But imagine this distance is very tiny, right? So first of all, let's establish a direction. So suppose the direction of motion, a change from the point P, is given by that unit vector, and let's actually sketch the unit vector. We won't need to sketch it in general, but for now let's actually sketch it in the component form here with green. So let's say this is the unit vector u, right, of components A and B. So this point over here is of coordinates AB. And we're going to need, like I said, to establish a tiny change from P in the direction of U. So from P, I'm going to draw a parallel line. Again, it's going to be exaggerated to another point Q. We're going to see the components of Q in a moment, in such a way that the length of this segment, right, if I measure it, is H. Right, the magnitude of that segment PQ is H. Right, that's the analogous to a change from x naught to x naught plus h in calculus 1. So a small change in the domain of the function in the direction of u. And then the question is, how does the value of the function changes for that particular change in the domain? So let's say corresponding to the point P in the domain, in the surface of the function, z equals f of x, y. Let's say this is f of x naught, y naught. And let's say, doesn't have to go up here, but just to see it better, and let's say corresponding to q, you have another value of the function. We didn't establish yet the coordinates of q. We'll get to that in a moment, right? But anyway, in this picture of mine, let's sketch the change in the function with blue. With blue is the corresponding change in the value of the function, and in red the corresponding value of the corresponding change in the domain in the direction of u. Okay, so how do I get the coordinates of q if the segment PQ should be of length h? Let's take a little bit of a detour, just for a little bit, from this picture. And notice that if you have to, let's actually go back to the vector in the component form here, right? So we have that vector like that in the component form of coordinates AB. If you want to increase its size just by length h, right, which is just increasing by length h, the new components will be AH and BH. This is a consequence of the length of this segment being actually 1. If you want to make, I take that back. So if you want a vector in the direction of AB to be of length h, in the direction of AB, okay, so let's say this is x, this is y, then its components should be AH and BH. Okay, to convince yourself why that's the case, notice that the magnitude of AH and BH, if you go with the formula for the magnitude, that's a squared h squared plus b squared h squared. We can pull h squared out of the radical. And because I chose a unit vector, and I hope you see the convenience of it, this is going to be h times 1. Okay, so again, in component form, if AB forms a vector of length 1, AH times comma BH will form a vector of length h. So now, going back to the vector PQ, how do I come up with a vector of length h, but now starting from x naught, y naught? I'm going to just simply add AH and BH. It's like translating the vector AH, BH in the component form from the initial point 0, 0 to initial point P. Okay, so add AH and BH over x and the y coordinate. So that means the corresponding value of f at this point will be f of x naught plus ah, y naught plus bh. We're almost ready now to establish the definition, and we'll get to the second page to see how we can compute it. All right, we're going to write the definition on the second page as well to be clear. But let's review, let's summarize one more time what we discussed on this page. Pick a point P on the domain of the function. Pick a nearby point Q, which is at a distance h from the original point. That means the components of Q should be x naught plus ah, y naught plus bh. Remember, AB simply provides the direction of motion from P to Q. It's a unit vector, don't forget, this has to be a unit vector for this to work. And on the domain here, on the graph of the function, we have the corresponding values of f at these points. So then the directional derivative, we're going to write formally the definition on the next page, is going to be the limit of the difference quotient given by these values. So it will be first of all denoted by d sub u of f at x naught y naught. So that's the formal notation for the directional derivative. You indicate the function, the point, and the direction of motion. And that's going to be by definition the limit as h goes to 0 of f of x naught plus ah, comma, y naught plus bh, minus f of x naught y naught, divided by h. Provided, of course, this limit exists. If it doesn't, of course, there is no derivative at the point in question. So let's move on to the second page, write this nicely, and then see how we can compute it in practice. Okay, so here's the definition one more time. It's kind of a mouthful. We don't have to say the whole thing all over again, but just make sure you understand all the components given in the definition, right? So a function, the directional derivative of a function at the point x naught y naught in the direction given by a unit vector AB. Definition is the same if the function is of 3 variables. You just have 3 components and the vector will be ABC, right? The 3 components. But let's see how I actually compute it, okay? Because in practice, remember, we don't actually find derivatives by evaluating limits most of the time. And the rule is pretty simple, but let's see where it comes from, because it's a simple and useful exercise on its own. Notice that on the right-hand side here in the definition, pretty much everything is fixed, right? The point in question, A and B, except H. You can think of H as a variable before you evaluate the limit as h goes to 0. So let's actually denote this quantity, f of x naught plus ah, y naught plus bh, let's denote it by some function g of h, like a function of a single variable. And again, try to understand why it makes sense to make this notation. The function depends on x and y, but once you evaluate it at that point, translated by this unit vector, right, in the direction of AB, again, a and b is fixed, x naught, y naught is fixed, h varies, right? So it makes sense to think of it, I mean, you can think of it as a function of a single variable. Notice also that using this notation, g of 0 is nothing but f of x naught, y naught. Because if I replace h with 0, then that's x naught plus 0, y naught plus 0. So if you look carefully, in fact, my directional derivative, I can view it as the limit of a difference quotient of a function of a single variable. So at this point, I usually ask the class to answer the question, and you should pause the video and ask yourself the question. According to the definition of the derivative of a function of a single variable from calculus 1, right, g of h, what would this represent, this limit? This is a difference quotient on its own, right? But what does it mean as a calculus, as a single variable function from calc 1? So I hope you realize, after you thought about for a moment, that this is basically by definition nothing but g prime of 0. So I'm supposed to basically differentiate g with respect to h and then evaluate that derivative at 0, and that will constitute the directional derivative at the point x naught, y naught. So how do we do that? Because, by the way, we have to do this in a more practical form, not via this extra function, big G of h. But we could use the chain rule that we learned in the previous section, right? So you can think of G that sits at the top, right? G, which is basically given as a composition of function of several variables. In other words, is f of x naught plus ah, y naught plus bh. But really, that means it's like f depends on x and y, and in turn, x and y are functions of h. So this fits the chain rule. If you think of f on the top, the chain rule for a function of several variables, which depends on x and y, which in turn depend on h, right? You could think of x as a function of h, y as a function of h, y naught plus bh. So that means dg dh, right, viewed as a composition of a function of several variables, like in this tree, according to the chain rule, is going to be partial f, partial x, again evaluated at x naught plus ah, y naught plus bh, times dx dh. And then followed by df dy. We follow the chain rule, times dy dh. One more intermediate step. We're going to copy the partials. We should have done this in one step. But anyway, so what is dx dh? Look at x of h. X naught a is a constant, so dx dh is going to be just a. Copy the second partial. And then dy dh is going to be b. But remember, what we want is g prime of 0, right? So you want this whole shenanigan at h equals 0. That is, remember, that is in fact my directional derivative that I want to compute. But what do I get then? If I replace h with 0, there's just one last step, right? So that means g prime of 0, which remember was the directional derivative of f at the point x naught y naught, is nothing but partial f partial x at the point x naught y naught, right? Because h0 makes it x naught y naught, times a, plus partial f partial y at the point x naught y naught times b. Furthermore, we can even write it in a more compact form. We can recognize, in fact, a dot product here. So directional derivative is nothing but the dot product between a vector formed by the partial derivatives at the point in question dot the very unit vector that we use to establish the direction of motion. Or if you want to use the index notation, which we probably do most of the time, you can say fx at the point x naught y naught, fy at the point x naught. No, let's do it from here. Doesn't fit. So fx at x naught y naught, fy at x naught y naught dot ab. All right, so let's pause for a moment. This vector of partial derivatives is a very important vector Okay, so the vector whose components are the partial derivatives of the function is called the gradient at f at the point x naught, y naught, and is typically denoted with an inverted delta, the gradient of f at the point x naught, y naught. There are several important meanings related to this vector. We're going to write down the formula for computation here before we move on to the second page. But in essence, let's wrap it up. The directional derivative, in the most compact form, you can write it like the dot product of the gradient at the point in question. Remember, evaluated at the point in question, dot u bar. It's as simple as that. So the directional derivative is given by a dot product of the vector of partials, also known as the gradient, dot the unit vector for which you compute the directional derivative. So before we move on to the next page, from this point on, it's very important to not get confused, right? Because obviously we just establish a different type of derivative, not the partial derivatives. But as it so happens, partial derivatives that we learned before are used in the computation of the directional derivative in any direction that you choose. So we're going to go over a couple of examples, obviously, so stay tuned for the next page. All right, so let's take an example. Suppose that a function is given by x over y, and we want the directional derivative of this function at the point 2, 1 in the direction of u given by 3 over 5, 4 over 5. You should always check to see if the vector is of length 1. If it's not, we're going to make it of length 1. So let's see. Notice that this magnitude of u, square root of 9 over 25 plus 16 over 25, which is 1. So therefore, there's no need to modify anything, and we can proceed with the formula. So it's pretty straightforward. You start by evaluating the gradient, which is given by partial x, partial y, in a vector form. In this particular case, the partial x is 1 times 1 over y. So it's 1 over y. And partial y is minus x over y squared. And then finally, we're going to evaluate. You can write this together with the unit vector, but let's just do it separated. So now we evaluate it at the point in question, 2, 1, right? So this is my x naught, y naught in the formula. Be very careful to plug in the coordinates in the correct position. So y is 1, so it's 1 over 1 minus x, which is 2 over 1 squared. So the gradient at the point in question is 1 minus 2. And then finally, my directional derivative will be the dot product of the gradient at that point, 1 minus 2, dot the unit vector, 3 over 5, 4 over 5. And let's finish the dot product. That's 1 times 3 over 5 minus 2 times 4, 8 over 5, minus 5 over 5, that's minus 1. So if in my analogy, with the hill, right, in the beginning of the class, if you move in the direction of 3 over 5, 4 over 5 in the domain, that means you descend by this slope. That's the slope of descent on that hill, because it's negative. Let's do an example in 3 dimensions, same idea, same formula. We don't have to write a different formula, just adapt it for 3 dimensions. So let's say the function is x squared yz minus xyz third. And then we need to evaluate the directional derivative at the point 2, minus 1, 1, so that'll be x naught, y naught, z naught, in the direction of, let's say, 0, 5, minus 3. Let's call it v. 0, 4, minus 3. I want 0, 4, minus 3. Okay, notice it's pretty easy to see that the magnitude of v is not 1. If I compute the magnitude, its magnitude is 5. In the computation of the directional derivative, you need to normalize the vector. So divide the vector by its magnitude, via scalar multiplication, that is, to make it of length 1. So the correct vector in the formula will be 0, 4 over 5 minus 3 over 5. And now let's compute the gradient, which is the vector given by partial x, partial y, partial z. Partial x is 2xyz minus yz third. Partial y is x squared z minus xz third. Always remember to pause and do the computation on your own slower if you want to, and then check with me. And then finally partial z is x squared y minus 3xyz squared. Especially in 3 dimensions, be careful to plug in the coordinates in the correct position. So this will be x, y, and z, right? X naught, y naught, z naught. So what you get here is 2 times 2 times minus 1 times 1 minus negative 1, 1/3, comma 2 squared times 1 minus 2 times 1/3, comma 2 squared times minus 1 minus 3 times 2 times minus 1, 1 squared. So if we clean up this a little bit, let's see what we get. This is a minus 4 plus 1, makes it minus 3. The middle component is 4 minus 2, which is 2. And finally, minus 4 plus 6, that's 2. So finally, the directional derivative at the point 2 minus 1, 1 will be the dot product between this vector, the gradient, and the unit vector u. So minus 3 times 0, 8 over 5, minus 6 over 5, that makes it 2 over 5. All right. So that is about computational aspect of the directional derivative. Let's go a little bit deeper to ask some other important questions related to this quantity. And in particular, let's see what is the actual meaning of this gradient, which is quite an important topic in calculus. So on the next page, I want to do this on the next page, but we're going to ask the question, let's say, and that's an important question. Again, let's go back to the hill analogy, right? Right? You walk on a hill. You're at this position here. The altitude is over here. You don't have to sketch this, but again, to use that hill analogy. Now we can compute the directional derivative if we move in any direction we want in the domain. But here's a question. Which direction provides the maximum rate of change for the function f of xy, or f of xyz in general? So in the hill, what is the steepest, with the hill analogy, what is the steepest direction? in what direction does the function increases the change of the increases the maximum, right? I mean, you have the maximum rate of increase of the function, in other words. So spoiler alert is going to be the gradient, but let's see where it comes from, right? So let's stay tuned for the next page. All right, so once again the question: direction of the maximum change of the function f of xy at the point in question, x naught, y naught. What is it? So you're at this point in the domain, and you're asking yourself, of all possible directions that will give me that directional derivative, which one gives me the greatest rate of change for the function itself? So the answer is actually quite simple if you go back to the geometry and some of the formulas we learned. So remember, from the way we computed the computational formula for the directional derivative, that's the gradient, which is a vector, remember? By the way, we don't put the bar on the top. I found that not necessary like that. Some people do it, which is fine. It's not a mistake. But since it's a special notation for the gradient, which by definition is a vector, it's not necessary. So the gradient dot u, right? That's the way to compute it. And remember, we're looking basically for maximizing this quantity. Now, remember that there is a formula which relates the cosine of the angle between two vectors and the dot product between the vectors. So these two vectors, if they form an angle, right? So let's say the vector u is here and the gradient is here at that point. Right? If you bring the gradient in component form, right? They emanate from the origin. They form an angle theta, and remember that formula, right, for the cosine of the angle between two vectors, which is u dot v over the magnitude of u times magnitude of v. So if we apply this formula and write the dot product on the top, it turns out that this dot product is nothing but the magnitude of the gradient. Pay attention here, the magnitude of the gradient times the magnitude of the unit vector u times the cosine of the angle between them. So because the unit vector is actually, well, as the name implies, it's of length 1, right? It's a unit vector. It turns out that any directional derivative is in fact given by, alternatively, right, by the magnitude of the gradient times cosine of the angle between them. So you can use that as an alternative formula to compute it, but of course it's not practical, because to compute cosine of theta you go back to the dot product anyway. So just to compute the directional derivative, the dot product is the efficient way to write it. But in fact it can be written as magnitude of the gradient times cosine of the angle between the gradient and the unit vector. When is this maximized? Well, the gradient at the point is fixed, right? That's a fixed quantity. Theta varies. That's the one that varies as u varies. I'm asking which u will work to give you the maximum. That's like saying, what is theta that gives me the maximum quantity? So ask yourself and pause the video, what is the theta which will provide a maximization of cosine of theta, assuming that the gradient is fixed, obviously. And so notice that obviously the maximum possible value for cosine of theta is 1. Right? In trigonometric function, the largest possible value is going to be 1. And when is it achieved? Well, cosine of theta is equal to 1 if theta is 0. In this way to compute the formula, remember theta is between 0 and 180 degrees, right? So the largest possible value for cosine is attained when theta is 0. Let's look at the geometry one more time. What does it mean for theta to be 0? Well, it means for u to be in the same direction of the gradient. Right? So now we can answer the question, right? If we compute the derivative, the directional derivative, in the direction of the gradient, we obtain the maximum possible value for this directional derivative. So it's in the direction of the gradient. We don't have to actually redo the formula all over again, right? Because you just have to remember that if cosine of theta is 1, all that's left in the computation of the directional derivative is going to be the magnitude of the gradient. So the gradient itself as a vector provides the direction of the greatest rate of change. The actual maximum rate of change is the magnitude of the gradient. For some reason, lots of students sometimes still find this confusing, and they make mistakes when you have, because you're going to have this type of questions, by the way. If you're my student, you're going to have it in the quiz or exams, and/or exams. But it's extremely straightforward. You just have to remember the interpretation of this quantity, the gradient. So let's actually write these remarks in a different color, right? So the gradient as a vector is the direction of the maximum rate of change of the function f of xy at the point x naught, y naught. But the gradient at the point in question, sometimes for convenience we won't write of x naught, y naught if it's clear from the context. All of this is at the point in question, x naught, y naught. So if the question is where would you move in the domain to obtain the maximum rate of change, you move in the direction of the gradient. The magnitude of the gradient is the actual value of the quantity above, is the maximum rate of change of the function at the point x naught, y naught, which occur in the direction of the gradient itself. Gradient tells you where you move to maximize the rate of change. The magnitude of the rate of the gradient is the actual maximum rate of change. And let's illustrate with another quick example. Something easy to compute. So let's pick a function of two variables, f of xy equals xy squared. And then we want, so at the point 3, 1, let's say we want the let's say we want to find the direction of the maximum rate of change and the actual rate of change. That's like asking what's the gradient, what's the magnitude of the gradient. It's as simple as that at the point 3, 1. So all you have to do to answer this direction of the maximum rate of change is to compute the gradient, which in this case is partial x is y squared, partial y is 2xy, again at the point in question, so at the point 3, 1, this will be 3 squared, which is y squared is 1, and then 2xy is 6. Take that back, so one more time. So the gradient at the point 3, 1 is gonna be 1 squared, because you plug in 1 for y, and then 2xy, which is 6. So the gradient is 1, 6. So that's the direction of the maximum rate of change. The actual maximum rate of change, the actual value, is going to be the magnitude of this gradient, which is square root of 1 plus 36. That's square root of 37. Square root of 37, let me actually approximate it with the calculator quickly, because I want to actually show you something real quick before we turn the page. Hopefully it's gonna fit. All right, so square root of 37, 1 second. It's approximately 6.08. Any other directional derivative is going to be lower than this. So let's do a quick alternative directional derivative. Let's say I choose the vector 3 over 5, 4 over 5. Let's do the directional derivative in the direction of u, which is 3 over 5, 4 over 5, whose magnitude is 1. We used this vector before, right? So 9 plus 16, that's 25. Okay, so that's 1. Okay, so the directional derivative in the direction of this vector, again at the same point 3, 1, is going to be again the gradient 1, 6 dot 3 over 5, 4 over 5. And if we do the dot product, that's going to be 3 over 5 plus 24 over 5, which is 27 over 5. And now approximately, if we use the calculator again, 27 over 5, that's going to be 5.4. So as expected, a lower quantity than the maximum possible, 6.08. So there are a couple of other topics to discuss before we call it a day. Stay tuned for the next page. Okay, so let's talk about the interpretation of the gradient a little bit more. By the way, this is obviously something that normally I cover in at least 2 lectures, so don't expect to cover this in one sitting unless you have the energy for it. Because this topic is very important, so if you're tired by this point, you probably can just pause the video here and then continue it later. But let's review one more time. Well, first of all, I want to make a connection with partial derivatives as particular cases of the directional derivative, just briefly. Just to kind of put everything together, right? Remember, if you have a point, let's say, if you want to compute, if you have a point x naught, y naught in the domain, and then you move in a horizontal direction, right? So, for example, you want a rate of change as you move in a horizontal direction. So that means you want a unit vector. Again, if you sketch the domain in the xy plane, you want a unit vector in the horizontal direction, right? If you want to compute the directional derivatives, if you move horizontally, so to speak, from your perspective, if you look at the domain here. Well, the unit vector along the x-axis is basically the standard unit vector, right? So that's going to be 1, 0. Okay, so what it will be the directional derivative according to my formula? Well, it's going to be the gradient at that point dot the unit vector 1, 0. But if you compute this dot product, not surprisingly, hopefully, you're going to end up with partial x. Because think about, again, just think about carefully, because it's very useful to fix the learning on the previous topics. How did we introduce the concept of a partial x? You keep y constant and you change x. So that is to say, you move on the x-axis, right? You move in a direction parallel to the x-axis, which is given now by this unit vector. So therefore, the partial derivatives is basically, the partial derivative is just a particular case of the directional derivative. In the same manner, you can view the directional derivative if you move vertically along the y-axis, which is given by the unit vector 0, 1. Unsurprisingly, you're going to end up with the partial derivative with respect to y. So now, obviously, it's useful to study partial derivatives separately because they appear by themselves, they are important, and also as part of the computational formula for the directional derivative. So that's one thing I want to say. Never forget in practice the meaning of the gradient. That gives you the way the function changes the maximum, right? The greatest rate of change. You will hear, for example, especially those of you who take partial differential equations, you will hear, for instance, the gradient, the space gradient, for instance, for heat transfer. For example, you don't have to sketch this, by the way, but if you imagine you are in a room and you have the points at various temperature, you have the heat flowing from a hot spot to a cold spot, right? And then, so basically the heat loss is toward the cold spot. And for example, if you want to check to see if a room is insulated well, or if you want to spot the points of where the heat is lost the greatest, it's like you're looking at the space gradient, and you can hear actually this terminology saying that, oh, I came close to this poorly insulated window and I can feel the gradient, heat gradient. In other words, you feel that near that point, the loss of the heat is the greatest. That is to say, if the function of several variables denotes the temperature at that point, the gradient of that function, so let's say f of x, y, z is the temperature, the gradient will give you the direction of the greatest heat loss, or heat gain, depending on the orientation, of course, of how you compute it, or how the how the value of that function is constructed. So that's one thing. Now, there is another interpretation of the gradient if you for a function of 3 variables. So that's another important topic, and that's going to be the last topic to discuss probably. But let's take our sweet time to go through it. There is a connection between the gradient for a function of 3 variables and the tangent plane to a surface. Tangent plane to a general surface. Up until this point, we talked about the surface in 3D as given as a function of 2 variables. So this is by default a surface, right? What we call by, the default graph of the function of 2 variables. But not all surfaces can be given explicitly as a function of 2 variables. Excuse me. You can also think of a general surface given as implicitly as a function of, as a combination of 3 variables, x, y, z. So you could have an implicit equation of a surface which is given as a generic function f of x, y, z equals to some constant k. Sometimes people would like to put k on the left side and keep 0 on the right hand side, so this constant here can be part of the function of 3 variables. Doesn't have to be, and I think it's, for my purpose today, it's probably useful to think of it that way. And as an example, we already had examples, right? I mean, for example, the equation of a sphere, for example, of radius 9, is an example of an implicit surface, right? So essentially, any combination of x, y, z, which presumably you can write it as a function of x, y, z equal to a constant, can constitute the equation of a surface. And I also remind you another concept we learned before. This is also called a level surface of the function of 3 variables f of x, y, z. Remember, one way to visualize possible values of a function of 3 variables, because we cannot sketch them, right? I mean, for a function of 3 variables, the 3-dimensional system is used to represent the domain, but the value of the function, it's a fourth variable. So that's not going to fit in the same 3D system. But you can visualize the values, the location of a given value, right? So for example, you can visualize where are all the points x, y, z for which the value of the function is equal to k. That gives you a surface, also named a level surface for the function f of x, y, z. So for example, for the function x squared plus y plus z squared equals 9, another level surface will be x squared plus y squared plus z squared equals 1, right? So all of these level surfaces are spheres, obviously. And so in general, if we were to sketch the just a generic sketch, right, like we did it before, suppose this is going to be the level surface, like I said, f of x, y, z equals k. And I want to give a meaning to the gradient. That's my goal on this page and the next one probably. So let's pick a point on the actual surface. And this is the point x naught, y naught, z naught. And suppose we're looking at a curve that goes through the point and is on the surface. So think of r of t. Let's say this is a curve r of t. A curve through the point x naught, y naught, z naught, and on the surface. F of x, y, z equals k. Now remember from previous chapters that a way to represent a curve is with a vector function, right? So therefore, you can view x of t, x, y, z as functions of a parameter t. And for my purposes here, it's not really relevant, the domain here. And just imagine a surface, a continuous surface that goes through that point. And then furthermore, let's say I'm looking at the tangent of that curve. So remember the tangent vector at the point, at the curve r of t, is going to be given by r prime of t, right? Which is nothing but the vector of partial derivatives. Excuse me, the x prime of t, y prime of t, z prime of t. Finally, we'll see where I go with this. There is a logic to it, trust me. Let's state mathematically what it means for this curve to be on that surface. It means that if I plug in the components of the curve, x of t, y of t, z of t, into the surface, I'm going to end up with a true statement, right? So f of x of t, y of t, z of t should be equal to k, right? So a curve included in the surface. And I want you to see this again as a composition of two functions. A functions of three variables, which in turns are functions of t. Because I want to differentiate this quantity with respect to t. On the left side, I'm going to have df dt. On the right hand side is 0, right? Because the derivative of a constant with respect to anything should be 0. Okay, now via the chain rule, what is df dt? Well, that's going to be partial x of big F times x prime of t plus partial y of big F times y prime of t plus partial z of f big F times z prime of t should be 0. But now I hope you guys notice that again, this is a dot product. It is a dot product between a vector of partial derivatives of big F and the vector of the derivatives with respect to t for that curve, x prime of t, y prime of t, z prime of t. In a more compact form, this is saying that the gradient of big F at that point, x naught, y naught, z naught, dot r prime of t should be 0. All right, so let's pause for a moment and let's see the geometrical interpretation of this result. So what did we establish? Let's go all the way back to the picture here, and then maybe use different colors. We picked a curve. Okay, let's in the surface, right? And then let's sketch the tangent to it by red again. Now, what we know about two vectors whose dot product is equal to 0? Geometrically speaking. Geometrically speaking, it means they are orthogonal. So the gradient of big F and that tangent vector are perpendicular. But I hope you guys notice here that there is nothing special about this curve. Okay, I could have done the same work by picking a completely different curve, at least around the point x naught, y naught. Here's another one with green. And I could compute again another tangent. And this time, that other tangent, well, I'm not going to name it anyway. So, and then the gradient would be perpendicular to that tangent as well. Okay, the gradient vector. So let me sketch the gradient vector with blue here to emphasize that the gradient of big F is going to be perpendicular to any tangent that goes through any curve around that point. All right, but if you pick two tangents at that point, right, which are not parallel, right, those two tangents, so those tangents that I sketched there, form the tangent plane. You need two of them, basically. Doesn't have to be partial x partial. I mean, remember, we did the tangent plane using the tangents that are along the x and the y axis. But in fact, any two tangents going through any two curves will determine the same tangent plane. So here's the main conclusion before we move on to hopefully the last page to see how this plays out in application. For a function of three variables, so for f of x, y, z, the gradient of this big F happens to be is the normal to the tangent plane at the point x naught, y naught, z naught for any level surface f of x, y, z equals k. So if you have a surface given by f of x, y, z equals k, the normal to the tangent plane at any point on the surface happens to be the gradient of that function of three variables. Why? Because it is perpendicular to any tangent, to any curve that goes to that point on that level surface. So that means we can find the equation of the tangent plane not just for the surfaces given by two variables, but for generic surfaces given implicitly in the form of f of x, y, z equals k. So let's actually use this fact on an example on the last page. All right, so here's the example. Find the equation of the tangent plane for the surface xy squared z third equals 8 at the point 2, 2, 1. Right, so you can check that 2, 2, 1 is on the surface indeed. 2 times 2 squared times 1/3 is equal to 8, as expected, right? So 2, 2, 1. So it's a surface given implicitly as a level surface. It's a level surface for the function big F of x, y, z equals xy squared z third. All right, what do we know about, first of all, so what did we establish before? We established that the gradient of f is the normal to the tangent plane. Let me remind you that the equation of a plane, let's put it here in a box, the equation of a plane whose normal is given by the components a, b, c, and that goes to the points x naught, y naught, z naught, is a times x minus x naught, b, y minus y naught, c, z minus z naught equals 0. So we have the point, we just need to compute the normal. What is the normal? The normal is the gradient, as I said. Compute the gradient, that's partial x y squared z third, partial y 2x y z third, partial z 3x y squared z squared. At the point in question, again, carefully plug it in into x, y, z. 2 squared 1/3, 2 times 2 times 2 1/3, 3 2 1 squared, 2 squared, sorry, and then 1 squared. So the normal is 4 8 24. So hard part is over. X naught, y naught, z naught is the point in question, 2 2 1. So the tangent plane is going to be 4 times x minus 2 plus 8 quantity y minus 2 plus 24 z minus 1 equals 0. And as always, it's customary to collect the constants for x plus 8y 24z, and then plus 8 plus 16 on the right plus 24 equals 48. And maybe we can just divide by, I think we can divide by 4 everything, both sides, so that gives me x plus 2y plus 6z equals 12. So that's the equation of the tangent plane at that point. All right, so I want to conclude. I find this very important. I want to conclude with a connection between another formula for the tangent plane, because it's important not to get confused and see how they actually blend together. This, what we get at this point, is a more general formula than what we had before. So remember, before, if the surface is given explicitly, and I ask the tangent at the point AB, and notice that basically the point really is AB f of AB, right? Typically the z coordinate is not given because you can always find it. Then the equation of that tangent plane was given to be z equals f of AB plus partial x of little f at AB x minus a plus partial y at AB y minus b. This is also used to figure out the linear approximation of the function f of xy at AB. People sometimes get confused between these two formulas because the partial derivatives that appear here have nothing to do with the partial derivatives in the more general formula that we established in this section. But they are related. One is just a particular case of the other. And so let's keep this in mind, and actually let's do a quick example with this formula from before, right? So let's say your function is this paraboloid, right? X squared plus y squared. And you want to compute the tangent at the point 1, 1, 2. Okay. So this is A and this is B, right? In my notation. And really 2 is f of AB. So partial x, okay, so in my case f of xy is x squared plus y squared. Partial x is 2x, partial y is 2y. And then we're going to evaluate this at the point in question, right? So therefore the tangent is going to be f of AB, that's 2. Partial x at the point 1, 1, that's really 2 times 1. Quantity x minus 1 plus partial y at 1, 1, which is again 2 times y minus 1. So with that formula, the tangent plane is z equals 2 plus 2x minus 2 plus 2y minus 2. 1, 2 cancels, and then z is going to be 2x plus 2y minus 2. Okay, so that's what you get if you apply the formula for the tangent plane for a function of for the surface given by a function of two variables. But you can view this function of two variables as a function of three variables, as a level surface of a function of three variables. So for example, I can move z to the one side of the equality, and I can think of this as another big function, big f of x, y, z. So really be careful here not to confuse big F with small f. So big F of x, y, z equals 0 is the same surface, but viewed as a function of three variables, as a level function of a function of three variables. And notice that if I use the equation of the tangent plane for a level surface that we established in this section, I'm going to have to come up with the gradient of big F, which is big partial fx, big Fy, big Fz. But what does that mean in my particular case? Well, big F partial x is going to be actually small f partial x, because z goes to 0, right? I mean, partial x of z is 0. Big F partial y is nothing but f partial y, little f partial y. And big F partial z is nothing but minus 1. And so when we actually establish the equation of the tangent plane in this case, you end up with the same thing, because now the normal to the tangent plane at the point 2, 2, 1 is nothing but partial x of little f at 1, 1, which is 2. Partial y at 1, 1, which is 2, and then this guy is minus 1. And then when you set up the equation of a plane whose normal is 2, 2, minus 1, going through the point 1, 1, 2, so the point, remember, is 1, 1, 2, well, you end up with 2x minus 1 plus 2y minus 1 plus negative 1 times z minus 2 equals 0. But if I rearrange the terms, you end up with the same plane. Z equals 2x plus 2y minus 2. So I want to emphasize that the formula for the tangent plane in this section is just the more general one. The one we had before, it's a particular case. It's still worthwhile to see it as a separate formula because it's more convenient if the surface is given by a function of two variables. And with that, that's it for today. See you later.